Hermosa, last year PhD student at the IAA in Granada. And I'm going to present our work, which basically is summarized under the question, how common are outflows in low-luminosity AGNs? So I had prepared a slide presentation about AGNs, but we have already heard about that. So just to be real quick, as you have already heard, basically there are many types of AGNs, but they are all believed to be the same objects under what is called the unified model. But the only real difference that we can find between some types of AGNs is essentially the level at which the accretion disk is feeding the supermassive black hole. So we can classify them between these, depending on this accretion rate. So we have very high luminous AGNs, which essentially are really high accretors. And then we have low luminosity AGNs, which are low accretors, and they are in the limit between systems inactive or non-active. Among them, we found what they are called liners. So the word liners stands for Low-Ionisation nuclear emission-line regions, which essentially means that if we look at their optical spectrum, we find relative intense low ionization emission lines with respect to other high ionization emission lines, such, for example, oxygen 1 with respect to oxygen 3, which typically is on the other way around for more luminous AGNs such as CIFER. So here you see the oxygen 3 really intense with respect to oxygen 1. The great things, or the most important things about liners, is that they are the most numerous population of AGNs in the nearby universe, and this basically allow us to actually study the physics of the AGN really nearby context. Probably the most hot topic in AGNs the last few years has been the outflows. So outflows are essentially gas that is blown out from the galaxy, from the host, due to the activity of the AGN. And they have been suggested to be ubiquitous within the AGN population, which means essentially that all AGNs go through a phase in which they blow out this gas. But this is a hypothesis that has not been tested for low ionization, low luminosity AGNs. And this could be basically bias, simply because we know that the power of the outflows is correlated with the power of the AGN itself. And so this means that for low luminosity AGNs, the outflows tend to be smaller and more difficult to detect. So what we want to do is to study if indeed outflows are also common in these low luminosity AGNs. So we started this work by selecting two samples, relatively small samples, of a total of 31 targets, in which we obtain optical spectra, long slit spectra, using both ground-based facilities and also HST data. So here you see how a typical spectra of these objects is like. And what we basically wanted to do was to fit the emission lines and try to see which kinematic components could better describe the emission lines that we are looking at. And what we found is that in 1/3 of the sample, this is 11 out of 31 targets, there was a component in the emission lines which was really blue shifted and quite broad. By quite broad, I mean velocities, with a maximum of about 1,000 kilometers per second. So these two characteristics, blue shifted and broad component, are usually associated to the presence of outflows, kinematically detected. But okay, we have now some sort of an idea of which percentage we are looking at, but still we have really few targets. So what we decided to do was to go for a more kind of systematic work and try to actually put more constraints on how common outflows are in liners. So we went for imaging data, and for that we used the NOT telescope. So, okay, it's true that outflows are better characterized and detected with kinematic information, but they can also be at least glimpsed only by imaging the targets. So here you have an example. I don't know if you can see it well from behind, but essentially what you see here is that the H-alpha emission of this galaxy really shows a nice bubble emerging out from the center, which is indeed an outflow that we are now characterizing with several field spectroscopic data. So there have been already 2 previous works that have started to take this approach to actually see how the ionized gas behaves in these targets. And what we have done now is to gather the largest sample that we could of nearby liners and try to observe this H-alpha emission, the ionized gas, and see how it behaves. So for that, we have gathered the data from previous works, and now we have the largest atlas of these ionized gas morphologies for a study of this kind. So all the data from previous work came from the HST archival, but 90% of the new data is coming from from the ALFOSC instrument. And the great advantage that ALFOSC had versus the HST that we also we heard about it earlier is essentially the large availability of filters around the H-alpha line, which essentially allowed us to actually select the best filter always to match the position of the H-alpha line in all our targets that are different redshifts. And then we also complemented our data with soft X-ray data just to see how well the 2 emissions compared. As for the data reduction process, it was pretty standard imaging reduction process, except that we did dedicated background subtraction just to ensure that we weren't introducing any particular structure into the morphologies of the H-alpha. This was really important because we actually are only focusing on the morphology of the ionized gas. So we didn't want to introduce anything that wasn't unreal. I'm not going to step more into this, but if you have questions, let me know. This is what it looked like, the image, the raw image before doing the subtraction, and this is how it looked after. It's much nice. And then what we did was to obtain not only narrow-band images, but also broadband images in order to subtract the continuum from the galaxy and just list us with the H-alpha emission. You have some examples of what we found. This is essentially the contours of the H-alpha imaging at a 3 sigma level. And so as you can see, we have a big variety of morphologies. So in order to constrain this and put some order here, we defined 4 different categories plus an additional one for the morphologies. So the 4 categories are these ones. So core halo means whenever we have nuclear emission surrounded by some diffuse emission, but essentially very nuclear. Then disk halo or disky, which is whenever the H-alpha emission was around the spiral arms or the galactic disk, these kind of structures. Then bubble, which is the one we are interested on, that is essentially when we see biconical or bubble-like structures emerging from the nuclei or asymmetric structures that could be hints of outflows. Then dusty, which essentially when we have a dust lane covering the center of the galaxy, and then we cannot actually say much about the morphologies. And whenever we couldn't firmly put any of these 4 categories for a galaxy, we find a 5th one, which is the unclear one. That essentially, is for all the dubious cases. So here you have some examples for each category. Always on the left panels, you have the H-alpha image of 3 sigma contours. On the right, you have what is called a subdivided image, which essentially is very useful to highlight some possible asymmetric structures in the galaxy that could help us to actually to actually understand what's going on. And on the center, you have the percentage per each category. So essentially, we found that the 2 largest categories of morphologies were bubble-like with 32% and core halo-like with 29%. And just to show you this, an example of what we mean by unclear, essentially that here the inner contours of the H-alpha emission could resemble to the galactic disk, but the outer ones are somehow asymmetric, so it could be a dubious case. But let's focus on the bubble-like, which are the ones we are interested on. And now the question was, okay, we have now some morphological hints about them having an outflows, but is there any kinematic information in the literature that could actually tell us more about if they are actually outflows? So we did a very extensive search in the literature for all the 70 targets. And what we found is that for 60 out of the 70, there was indeed kinematic information in the literature. Half of them was coming from interval field spectroscopic data. And from those 60, what we found is that 29, this is half of the sample, had a detection of an outflow in any of its phases, not only in the optical range, but also in other ranges. So what this is telling us essentially is that we have a potential detection of outflows of 50%, which is a bit larger, slightly larger than what we found in our previous works. What we did next was to compare how well the morphological information agreed with the kinematical information, that of course we know that it's better for actually detecting outflows. So here in this plot, I'm showing the morphological classification per each class, so core halo, bubble, disky, dusty, and clear. And here the percentage of kinematic detected outflows. So as you can see, basically for all except for the disky one, we have a 50% of detection for each category. So the disky one, we found it in the lowest percentage, but this could be also because of orientation effects. So we have not put any constraint on the orientation of the AGN towards us. And so maybe we are missing some outflows because, of course, morphologically, the orientation actually has a place. As for the X-ray emission, well, they have been proposed that H-alpha emission and X-ray emission should be produced in the same regions of the AGNs, and they should then be found as co-spatial. So in our sample, what we found is 60% of coincidence between both emissions. So here you have continuum of one of our galaxies, here the contours of the H-alpha, and here the contours of the X-rays, and you see that they match quite nicely. Okay, so what now? We have put some numbers on this, but still we do not have kinematic information for all of our targets, and of course, we do not have it systematically. No? We are only considering data coming from the literature. So what we are doing now is going for interval field spectroscopic data. So we have gathered data for a total of 12 targets with Megara at the GTC telescope. And we have started by with one galaxy, which is NGC 1052, which is a very prototypical liner, for which we have gathered data not only with Megara, but also with Muse at the BLT. And we have found a really nice outflow that we have characterized perfectly, so this work is already published. And now we are working with the other 11 targets to see if we can put further constraints on the percentage that we have found. But essentially, this is the first time that we could put a number, at least some initial number, on how common are outflows in AGNs. And of course, this work has only started, and let's see what the IFU data show us. And that's all. Thank you.